today we will start with the dynamic modeling of generic robot manipulator. So far we have not discussed or anything talked about in the framework of mass or inertia, because it was this. But in this chapter we will also include, if at all, the manipulator has certain mass or inertia. We'll take up the same example, the 2R serial manipulator, and we'll do the dynamic modeling for the same. So let us suppose I have the same 2R manipulator. But essentially, now this possesses mass 1, and the center of mass of this link is at the middle of this particular link, both the links. Okay, so this is your mass 2, link length is L1, link length is L2. My theta 1, and along this I have theta 2, and the mass is concentrated here, as if you have a massless link throughout, but all the mass is concentrated here. And this is the assumption that I am making. Mass is not equally distributed. This is concentrated on middle of this part for the sake of simplicity of the dynamical equation. Okay, so first let me define what is dynamics. So dynamics is the dynamical behavior of manipulators is often referred to dynamics is referred to the equation of motion with input torques or forces. So torques, if there are motors involved here, so whatever torque you have at these joints of those motors, so I am making torque 1 here and I am making torque 2 here. Okay. With the input of these two torques, what dynamic behavior that it shows means what is the angular acceleration, what is the of this link and that link, all sorts of things. So dynamics is referred to the equation of motion, that is precisely angular accelerations with that of input torques or force. So why torque force? It could be, joint could be of not prismatic sense, so that time it should have linear forces. Okay, since this is revolute, so motor must be attached in order to move that, so that is why torque. But in generic sense, it should have torque or forces. Okay, so the framework that we will talk about. So there are two frameworks that can lead to the dynamical equations. One is Newton-Euler framework. Another is Lagrange-Euler framework. This works on force balance, and this works on energy. So this is energy based. energy based formulation. The force balance or Newton-Euler formulation is quite cumbersome. Proceed. This is somewhat easier, and people use this formulation as long as hand calculation is concerned. However, when it goes to the coding or the recursive method of finding those things, this is more prioritized. But since we will be doing the hand calculation, so we will go by this Lagrange-Euler formulation in order to get the dynamical equation for this method. Okay. So now let's talk more about what is Lagrange-Euler formulation. So for Lagrange-Euler formulation, so this is based on energy. So we define a Lagrangian. We call it as Lagrangian. We define Lagrangian in the sense that Lagrangian is a quantity which is nothing but kinetic energy, overall kinetic energy minus overall potential energy. This is my of the system. Kinetic energy and potential energy of the system. This is how it is defined. Now, so every system try to minimize its overall potential energy. In that sense, an equation has been developed and which reads something like this. I'll directly write the equation. Okay. The equation reads as time rate of change of dou Lagrangian by dou Qi. So Qi is nothing but the torques and the forces that it is acting. So this is Qi's are the generalized joint variables. Okay, so Q1 means theta 1, Q2 is theta 2, Q3 might be theta 3, D1, D2 also will come, but in generalized sense. So in generalized sense, we will write it as Q. So D by dt, D Lagrangian by dQi, to be precisely, it is Q dot here. Please make a note, Q dot here, minus dou Lagrangian by dou Qi. This must be equal to the torque, the generalized torque or force that is acting. So I will write in generalized sense tau I, where I is equal to 1, 2, 3 dot dot n, if at all it is having n degree of freedom. Right now we have 2 degrees of freedom, so I will iterate from 1 to 2. So from where it comes, this is the mathematical part. So it has, again you have to go to mathematics and you have to check. But we'll take this as a granted that we have a Lagrangian equation, and we'll make use of this Lagrangian equation in order to find the dynamics of this. Okay. Now we'll proceed with the actual example. This example, we'll take mass, length, theta 1, theta 2, tau 1 and tau 2, and we'll proceed with this, and let's try to find out the dynamical equation. Let me rub this. So what is the meaning of inertia? To remain in its own state. Thank you. unless and until it is acted upon by something, so it will not move. So thank you. That is fine. So okay. So this Lagrangian is made up with these two quantities, K and P, right? So we have to find the kinetic energy of the first link as a system and the potential energy of first link as a system. Then I have to subtract it, and that would be my Lagrangian, and then it would be inputted in this equation, and we'll get one dynamical equation for this. Similarly, for this guy, it will have certain kinetic energy, it will have certain potential energy at some moment of time. Then you have to take that Lagrangian, put it here, and you will get second equation. This is how you do it. Okay, so first I have to find K1. Okay, so more precisely, let me write it once again. So more precisely, overall Lagrangian of the whole system. I am really sorry, not individually, because there is no indices here. You have to calculate overall system's Lagrangian in one shot. Then the indices are here. So let me rephrase it. So overall Lagrangian would be kinetic energy of first system plus kinetic energy of the second link of the system minus potential energy of the first and potential energy of the second link. This is how you will find the overall Lagrangian. And then once you find this, you plug it in and you start writing equation based on the indices. ठीक है, पहली बार आपको थीटा 1 से आपको यहाँ पे डिफरेंशिएट करना है, यहाँ थीटा 1 डॉट से, and दूसरे इक्वेशन में थीटा 2 डॉट से, and then you will find represent. ठीक है, please keep in mind. Okay, so what is next? So first one to find. So what are these things? K1, K2. So individually we'll try to find. So what is my K1? So I know it has certain mass, and it is a lumped mass here, and it is trying to rotate. So it will have two things. You have half mass times velocity square, will be 1. Let's talk about 1 plus half I omega square at that moment of time. So omega is nothing but the theta 1 dot square. Okay, यहाँ तक सही है? Fine. Okay. Now how to find I? First thing is here is how to find I. Yes. This is the moment of inertia of a rod. So let's suppose I have a rod. Let me do this exercise for the sake of clarity. And I want to evaluate the moment of inertia at this location. So let's suppose this is having mass. What is moment of inertia, by the way? It is the rotational inertia or rotational laziness. So linear inertia is linear laziness. Linear velocity में जाने के लिए आपको जो laziness है, that we call it as linear inertia or mass, simple mass. Moment of inertia is the rotational laziness. When you try to rotate it, it doesn't want to rotate. So in that sense, more precisely in formula sense, it is the mass distribution from axis that will decide its inertia. How far it is, I mean how it is distributed throughout the axis. So that is why mr square. So moment of inertia is usually written as r square dm integrated over all the masses. ठीक है, let's suppose you have mass 1 here, mass 2 here, 3, 4, 5, 6, 7 and सभी का r1, r2, r3 पता है आपको, तो सभी को जोड़ के so mass mr1 square plus m1 r1 square, m2 r2 square, and all those things clubbed together we call it as, but in integrated sense we write it this way. ठीक है? Okay, so let me find it a priori. So let's suppose we have the formula also, but let's try to do this also. So let's suppose this from r distance, this guy have dm mass. ठीक है, तो overall mass is, let's suppose capital M, और मैंने okay, and the total length is L. So since L length का मास m है, so dr length का मास क्या होगा, m by L dr, if I'm not wrong. So this dm mass का जो वैल्यू होगा m by L dr होना चाहिए. हाँ, so now I'll put this dm into here. So moment of inertia is what? Integration of r square dm is what? m by L dr, and where the integration should go? This is from 0 है ये, so plus L by 2 to minus L by 2. Okay, so mass, this mass is constant, m by L बाहर, r square dm minus L by 2 to plus L by 2, m by L r cube by 3 minus L by 2 to L by 2. एक आदमी कीजिए तो कितना आता है?
dm के रिस्पेक्ट में इंटीग्रेट करें
dr टाइम वेरी नाइस. हाँ बताइए तो कितना आता है? m by L
cube by 8
हाँ?
cube by 8
m, so 3 भी बाहर कर देते हैं, let's suppose. So L cube by 8 minus plus हो जाएगा L cube by 8. This is 2 L cube by 8 by 4. So 1 और ये स्क्वायर हो जाएगा. So 1 by 12 m L square. So this is what we know the formula. हाँ, so अभी यहाँ पे हम क्या लिख देंगे straight away? Half m1, हाफ तो रहेगा m L1 square है ना, divided by 12 beta 1 dot square. Now what about this guy v1?
सर r ओमेगा लिख सकते हैं, और ओमेगा अगर वेलोसिटी है तो
हाँ वो भी कर सकते हैं, but I have one more way to do this. We'll do it in terms of theta in this way. So let's suppose the momentarily at this theta 1 angle, this coordinate is x1, let's suppose x1 y1 for the time being. That midpoint position is x1 y1. So velocity 1 square is nothing but x1 dot square plus y1 dot square, if I'm not wrong, होली. बाकी वो रखना है मेरे डेस्क पर. So this is what x कोऑर्डिनेट का टाइम डेरिवेटिव, y कोऑर्डिनेट से इसका कंपोनेंट होगा ना. दिस इज द मैग्नीट्यूड, दिस इज द मैग्नीट्यूड. अभी वेक्टरली सेंस में सकते हैं, दिस इज द मैग्नीट्यूड. सो x कोऑर्डिनेट का टाइम रेट ऑफ चेंज ऑफ जो भी होगा x कंपोनेंट,